Good morning, everybody. We are going to start off this morning with a sponsor talk from one of our platinum sponsors here at useR. So I'd like to welcome Maria Paula and Ignacio from Deloitte.
Hello, everyone. My name is Ignacio. I'm here with Maria Paula, and we are going to talk to you about our journey at Deloitte Economic Advisory. So a lot of you know Deloitte. Deloitte is a very big company that offer auditing and consulting services for different type of industries. It is present since at least 100 years, and it is present all over the world. And Deloitte Economic Advisory is a team that sits within Deloitte France. And we do economic consulting. So as economic consultants, what we do is that we use economic theory and data analysis in order to answer business and strategic questions. So we can address questions like touching competition policy, like if we want to know if a merger is likely to lead to significant increase in prices, things touching, for example, network and regulation, like what type of market design would elicit an optimal electricity demand response, or things touching impact analysis or public policies, like what kind of local economic benefits can Toulouse anticipate from hosting another sporting event. We work for clients like businesses, regulators, competition authorities, and other type of government agencies. So in order to do our job, we need a broad idea, two types of skills. We need economics, so economic theory, and we are needing more and more data science. We are going to tell you about one of these cases in which economic consulting is using every time more and more data science tools, and it is when we want to assess the effect of mergers. So let's think of supermarket mergers. Think about all the supermarkets that are around your house, and imagine that two supermarket chains decide to merge. So the competition authority will definitely want to clear this transaction before it actually happens. So on a broad idea, the competition authority will like to see what is the effect on a global national level, but it's also going to check the effect on a local level. And in our example, this would mean that the competition authority would like to know if around your house these supermarkets will still have enough competition or competitors, other supermarkets will still be there, that would not allow them to unilaterally increase prices. So in order to do so, as economic consultants, we would like to analyze local market levels analysis. So this will mean that we will have to check what happens in every supermarket of the target supermarket chain. And this means for us a report, expert report to the competition authority, but also tons and tons and tons and tons of maps and tables with the local market analysis. So this is something we do a lot, and this is how it looked in 2012. So in 2012, when we started doing this, we used to import data with Stata and treat them in Stata. Then we used to calculate distance matrices using OpenStreetMap request on our servers, and then we used to use QGIS in order to do these maps. So in 2013, we moved a little bit of this workflow to R, specifically all the things regarding creating the maps. So we were feeling a little bit better, and in 2016, we constructed our first R package that was a wrapper around one API that helps us to calculate distances. So the whole issue before was that we were coming back and forth from different tools, and every time that we needed to study a different configuration, we needed to update hundreds and hundreds of tables and maps, and it was a disaster. But since we think we have gotten better. And in 2016-17, we introduced for the first time Shiny apps with merger proceedings with the French Competition Authority, and it was really, let's say, a really update and upscale, because Shiny app is easy to use. The lawyers and the Competition Authority can check all the parameters and can see the results right away, and they don't need us anymore to update maps, tables with all the errors that this can happen. Shiny was good for the clients, but it was also good for us, because it let us a little bit more time to think about the actual merger and to start offering other things like optimization around divesting supermarkets. So maybe the merger is very complicated, and the Competition Authority will ask the merged supermarkets to sell some supermarkets. So now we are able to do more. This for that part.
Okay, so Ignacio presented how our journey looked for our clients for this type of cases, and now I'm going to speak about how it looked for us internally. So one of the challenges that we faced was learning R. So basically, we identified these 3 core areas that we needed to work on. So for data literacy, economists, we use statistics methods that are called econometrics. And what we had in 2016 is a team that already was pretty comfortable in these methods. We do a lot of data analysis. The standard in economics has been Stata. So at the time, the team was very comfortable in Stata, and there were some R users, but they were pretty much self-taught R users, and they were working in isolation. Then we knew about best practices that were being used in industry. We knew about version control, we knew about collaboration via GitHub, GitLab, and we knew about reproducible reporting, but it wasn't things that we were doing on a day-to-day basis. And then we knew we needed to get better at communication, both externally with the competition authority and with lawyers. As Ignacio showed, Shiny was a great way of improving that side of communication. And then we also knew that we had to get better at communication internally, so that meant documentation and knowledge sharing. At the time, I wouldn't say that we were completely bad at it, but it varied very much by team and by case. So this is how we are today. So we really put a lot of time and effort into teaching R to our staff, especially incoming staff, junior staff. A lot of this was because we were able to draw inspiration from the community and from all of the open source resources that there are. We also became better at following best practices, so we started learning Git, we started learning how to collaborate via GitLab, that's the service that we use, and we started using reproducible reporting at every stage of our process. So even when we just get a file from the client and we just do some basic statistics, basic data analysis, all of that is done via R Markdown. Then in communication, we got very good at communicating with lawyers and competition authorities, and that really is a testament of how friendly and Shiny is. So that also allowed us to maybe have a little bit more leeway in the other type of analysis that we submitted to them. Before the standard was Stata, now more and more they accept R as an annex or to do some other types of analyses. And now in documentation and knowledge sharing, that is one of the places where we're still working very hard at. So we have done some standardization. We have now created a workflow. We require all cases to have a README file, but we are still getting better at it. We're trying to install a knowledge repository, because since we are working with mergers and these are very confidential operations, generally, for example, if I'm working on a case, Ignacio might not even know who my client is or the specifics of the case. So we cannot have open source within our company. So the second challenge that we identified was that of mindset. So I think no one here is a stranger to flame wars, and the flame war in economics is Stata versus R. So we had a team that was pretty confident in Stata, and at the beginning it was difficult to get them to embrace R and moving some of their workflows into R. So one of the things that we think we were successful at was creating a workflow that was friendly both to our new R users and to the Stata users that we had at our firm. A second challenge was adopting an engineering mindset. So we come from social science, economic consulting. Economic consulting is in this weird place between academia and industry. And we needed to adopt this engineering mindset about testing, writing functions, for us to be able to do more and more sophisticated data products. And then this third challenge regarding mindset came with the exchanges with regulators. So getting them to embrace new products in R, getting them to embrace Shiny. And we were pretty successful at that. But it's still a work in progress. Like, we still need to do a lot of things in Stata. So it's both. So the third challenge has been that of growth. So for us, growth means doing our job better and faster and more robustly every time. So we're trying to standardize our workflows. This is not as straightforward as it would seem in consulting because we're constantly changing cases. So generally, our cases will not last more than 2-3 months, and then we switch industries, so it's very varied. And then we're trying to build more internal packages, more on the optics of optimizing our workflow. And then we are trying to innovate. So basically, the way that we innovate is bringing data science into economic consulting. We are economists at heart, and this is the type of job that we like doing. And that's what we're trying to do now, bringing more data science tools and data science methods into economic consulting. So thank you very much, and we would be very happy to answer your questions if we still have some time to do it. Thank you.
What type of framework do you use in data analytics? For example, do you use Agile or like the 7-step process of Chris DM? Can you tell us a little bit more about that, please?
Okay, so basically, as I understand it, you're asking how we are doing project management in the analytics side. So for now, our biggest challenge has been moving into GitLab and establishing this Git workflows. So right now, we're basically pretty much moving our our project management into GitHub issues. We haven't integrated with other platforms yet. The team is pretty small, like I didn't mention, but we're 5 full-time R users, I would say, and then with maybe 10 more in the making. So for now, we haven't reached that scale. But thank you for your question. Thank you very much.
Okay, while we're getting set up here, we'll get ready for the next keynote session. So I'm Andrea Rao. I am a statistician at INRA, close to Paris, here in France. And today it's my very distinct pleasure to introduce our 5th keynote speaker, Dr. Bettina Grün. I hope I said that more or less right. So Bettina is an associate professor in the Department of Applied Statistics at the Johannes Kepler University Linz in Austria. Her core research interests include finite mixture models and their use in model-based clustering, which is a topic that's near and dear to my heart and a part of my own research as well. She's focused on various facets of this area of research, including estimation, implementation, and application in a pretty wide variety of fields from marketing to tourism. To date, she has co-authored more than 50 journal articles and 7 R packages that are on CRAN, including the Flexmix package for flexible mixture modeling, which is a very well-documented and complete and extensible package that has been quite enjoyable for me to use. She's also editor-in-chief of the Journal of Statistical Software. And today, she will be sharing her expertise with us on tools for model-based clustering in R. So as she speaks, don't forget to use Slido to ask your questions for the end of the session. And please join me now in welcoming Dr. Bettina Grün.
Thank you very much for the nice introduction, and I'm glad to be here, and I want to talk today about this core research area. As Andrea has been telling you, I've been working on mixture models for a long time, and I thought I would take the opportunity when I'm standing in front of so many people today to talk about the work I've been doing now for sort of decades and share my views and ideas and what I've been observing in the last years about these kind of things. So the topic is model-based clustering, which is a part of cluster analysis. And cluster analysis sort of is a task which tries to group objects, and you try to put objects which are similar together, and you want to group objects which are dissimilar in different groups. And at the end of the day, a lot of cluster analysis aims at coming up with a partition of your data. So you have a data set, and then you partition it, you get some subgroups, and then this gives you sort of an idea what kind of structure is in your data set, and you learn what might be in there. And there have been different statistical methods proposed to perform this task of cluster analysis. And one side are heuristic methods, which is like hierarchical clustering, partitioning methods like k-means. And there's also this other field of model-based methods, where my focus will be on finite mixture models. If you want to do cluster analysis, the first thing you note is it's sort of an ill-posed problem. Like, what is a cluster? If you show someone a picture of data, normally two-dimensional, people visually see what a cluster is. But coming up with an idea of formally defining what makes a cluster, which is something you need if you want to get it back from an algorithm. You have to tell the algorithm what kind of structures are you after, what should your cluster look like. So you need to formalize the idea of what a cluster is, and there have been different notions proposed for what a cluster could look like, what a cluster could be, what kind of structure you're looking in your data. And one is the feeling of compactness. So if you look at your two-dimensional scatter plot, you would want to have like groups of points together which form compact sets, and these you would identify as clusters. Another idea is, like if you do a density estimation, you look for areas where densities are high. That would be more a density-based level method of identifying clusters. And this means they could have different structure. A cluster which you define through compactness should have different characteristics than a cluster you define through density-based levels. Another idea was having connectedness. So if points are, like you have a sequence of points which are close together, they form a connected set, and this in the end could be a cluster in your view. And there is also the idea of points sharing sort of functional similarity when you come from a regression setting, and then you want to put points together or observations together where the regression relationship is similar. And this also means, depending on how you define your cluster problem, you might get different cluster solutions. So in some sense, there is no true solution, and people say whatever looks like a useful solution is the thing you're interested in, whatever tells you more about what the structure in your data is. And you can try out different concepts, come up with different solutions, and then move on. And it's often the application context where you need to talk to the domain expert and ask them what kind of clusters are they after? What do they want to use the partition for afterwards? Do you want to have a centroid, one typical object in that group to characterize all observations in that group and move forward? So that would be a different task than looking for other clusters. And I tried to come up with a visualization of these different concepts. And I think the one on the left, that's like the prototypical. That is compactness. If you look at it, you directly see there are 3 clusters. They all have the equal size. They're equally compact. And if you think about k-means, it will have no problems of finding these 3 clusters. So this is the easiest solutions. There are gaps in between. You could also have a density-based concept and you would retrieve them. Whereas the second example, this is prototypical for density levels. So you have still 3 areas where the density is higher, but they differ in their level of compactness. And k-means might have a hard time to find these 3 clusters. But with a suitable mixture model, we might be able to extract this structure from the data. And the third one sort of visualizes more of a set of connectedness. So if you look at it visually, you can see 3 groups of connected points, but coming up with an algorithm which captures that and also brings back this solution is not that easy. So what do model-based cluster methods do? If you pursue that approach, you embed sort of the clustering problem in a probabilistic framework. So the idea is you have a statistical model and which opens up the statistical toolbox. And you can use any methods we have been trained as statisticians to use. We can use inference on that. And we can also try to come up with statistical models which suitably capture our notion of a cluster. So in some way, specifying the model forces us to think about what's a suitable cluster distribution. But in some sense, it also helps us to explicitly do so. Often people feel if they use an algorithmic method, they don't impose any structure. This is sort of free of assumptions. But if you look closer, also k-means has certain assumptions on the shape of clusters it's looking for. And people often are not that aware for these algorithmic methods. Then if you pursue a model-based approach where you explicitly sort of formulate what the cluster distribution looks like. And this sort of helps you also in moving forward in deciding, did I specify a good model for the data? And if I then come up with a solution, any solution sort of will reflect information in the data, but also structure imposed through the model we have been specifying. And often putting these 2 pieces of information together is important to come at correct conclusions. So what does the data generating process look like in finite mixture models? So the idea is we have this partition. So each observation comes from one of k groups. So if you think about it in a data generating process procedure, the first thing you do is for each observation, you draw the cluster membership. So you draw from a multinomial distribution from which cluster is an observation, and then once you know from which cluster it is, you can condition on it and draw from the cluster-specific distribution. And that would be conditional on knowing cluster membership, so you have this hierarchical specification. If you integrate out sort of the cluster membership, the unconditional distribution would be a convex sum over the groups, a convex sum over the cluster sizes and the cluster distributions. And if we fit a finite mixture model, the thing we need to decide, or all finite mixture models sort of differ in what cluster distributions do I specify. And that's, in my view, the beauty also of this approach is whatever statistical model you know, you can make a mixture out of it. Like, you can always generalize whatever you have. You have a parametric distribution, and you can make a mixture of these parametric distributions. And you have a model, and you can make a mixture of these models, trying to capture sort of latent groups which might be present in your data. And the question is also, do you have just the y, or do you have also additional data, like x variables, which you could use in a regression setting for fitting? And if you're fitting finite mixture models, normally people need sort of decide on, do you want to pursue a maximum likelihood estimation approach, or do you want to do Bayesian estimation? And each of them comes with different problems and challenges, to put it that way. And if you want to do it in R, you can use both approaches, and you'll face the same problems and challenges, and you'll find a lot of packages also out there which might help you in addressing these problems. So if we want to use it for cluster analysis, what we also then need to do is like creating a partition or assigning cluster membership to the observations we have. So once we have fitted our mixture model, we can use it to determine the a posteriori probabilities, and we can then use these to assign observations to the group where the a posteriori probability is maximum, or we can just draw from this distribution to get a hard assignment, which then ends up with a partition. And if we use this for our 3 example data sets, if we select sort of a suitable finite mixture model, and then we assign hard with the maximum a posteriori probability, we'll get the cluster structure back. So our mixture models would have been able to identify exactly these 3 groups in all 3 settings, which we would have visually seen. So how do we estimate a finite mixture model? If we do maximum likelihood estimation, it's the EM algorithm, which has been proposed sort of in the 70s for mixture models, and since then has been used for all kinds of different models have been extended, different variants have been developed, but it's sort of the general algorithm which can be applied. An alternative would be to use general purpose optimizers. You just create the likelihood and try to maximize it, but the mixture likelihood is sort of not looking nice. In general, it's multimodal, and for many mixture models, it might also be unbounded. If you think about the parameter vector, it might be quite high dimensional, so general purpose optimization is difficult. And also in the sense, if you think our mixture density is a sum, if you take the log of sums, normally it is also not too good. So what people sometimes do is they try to use hybrid methods where they first start with an EM algorithm, which tries to bring you close to the maximum likelihood estimate, and then they switch to general purpose optimizers because they might have a higher rate of convergence. The EM algorithm is known to be quite slow in converging, in particular if close to the optimum. And for Bayesian estimation, there is no conjugate prior for the mixture model, and so the posterior is also not available in closed form. What people do is they use Markov chain Monte Carlo methods, and there has been a procedure proposed to do data augmentation. In some sense, everything would be easy in mixture models normally if we had known the cluster memberships. So this is the step you do in Bayesian estimation. You add it as a latent variable, as another parameter sort of. You're also drawing through your MCMC sampling, and you can use general purpose Gibbs samplers then in this context to estimate a Bayesian mixture model with Markov chain Monte Carlo sampling and data augmentation. And one possibility would be you could use JAX with the RJAX package. So how does the EM algorithm work? EM algorithm is a standard procedure in a missing data setting. And it has nice properties in the sense that because it increases the likelihood in each step, it converges if the likelihood is bounded. But we are sort of, because we're locally always increasing, it will only converge to a local optimum, so initialization might be crucial, or we need to try out different initial values. And we have also, it has always often been observed that it's slow in convergence. And if you look at the structure, the EM algorithm is sort of a framework which works for any kind of mixture model, and the main structure stays the same. You start with the E step, where you say, okay, we're in a missing data setting, and equally, in some sense, I feel the EM algorithm and Bayesian estimation with data augmentations are very, very similar. In the idea that you add the thing you're missing, the cluster membership, you say, if I had observed it, life would have been so much easier. And this is what you're doing in the EM algorithm. You use the complete data log likelihood, including the observations and the cluster memberships, and in the E step, you take the expectation of that to get rid of the things you haven't observed. And because here you get something which is linear in the missing data, essentially the only thing you need to do is to calculate the a posteriori probabilities. And you can plug that into your mixture model, sort of replace the class memberships you haven't observed with their a posteriori probabilities, and then the M step just consists of weighted maximum likelihood estimation. And in some sense, whatever model you want to fit, if that model you want to fit, you know how to do weighted maximum likelihood estimation, implementing the EM algorithm is sort of straightforward, and the main structure will stay the same. And this is a similar characteristic shared with MCMC sampling. So you data augment, and you also need to calculate the a posteriori probabilities, but then you don't take them directly, but you draw from them. So you get a hard classification, and then you move forward, and the similar step to the M step, you're not maximizing, but you're again drawing from the posteriors. But also this step is sort of, once you add the drawn cluster memberships, you're in a setting which is the usual setting if you want to fit that model without a mixture structure. So you can sort of reuse methods for that model which have been developed for Bayesian estimation. And where the EM algorithm is slow, we observe often that the Gibbs sampler has poor mixing. So we know the likelihood is multimodal, using symmetric priors, which would be sort of a usual guess, a usual thing to do in a model-based clustering setting. So you have a symmetric prior with a symmetric likelihood, you end up with a symmetric posterior, which also has different modes. And what people observed is MCMC sampling stays around one single mode and doesn't visit all modes which are present, which is sort of an indication that it's poorly mixing and that it might not have converged, sort of. These are procedures people are using if they fix the number of components, and for each number of components you can get a different fitted model. But in a model-based clustering context, often people don't know how many clusters there should be, so you need to decide on what is the correct number of clusters, or which model do you want to now select and move forward. And selecting the number of clusters sort of is still an open issue, I would say. It hasn't been resolved so that everyone agrees on this is a good solution. And I think there has been now a recent handbook on mixture analysis where they wanted to write a chapter on how to determine the number of components in a mixture model, and they ended up adding to the title perspective and strategies, because they found out they could just come up with possible strategies to pursue, but they couldn't come up with a solution which would be generally accepted. But there is certain standard methods which are usually used, and the easiest, computationally also easiest, is using information criteria. People like to use AIC and BIC, and then they're sort of disappointed because the aim of these methods normally is to get a good approximation of the density, which often is not a good solution for a clustering problem, because you might end up having too many components. And that's why also these ICL criterion was introduced, the integrated complete likelihood criterion, which tries to penalize for overlap in clusters. So you want to have a crisp solution that it will be pretty clear to which cluster an observation belongs, because then if you finally partition your data, not much information is sort of lost. And then you could also do the general things we're used in model comparison. One thing would be likelihood ratio test, but asymptotics do not really apply because you're at the boundary of the parameter space. So then it has been proposed you might use bootstrapping to approximate the distribution under the null. So that's, again, sort of computationally intense. And in Bayesian estimation, a usual choice would be marginal likelihoods, but that's also a very tricky problem to solve, calculating marginal likelihoods for the mixture model, and doesn't work too well with too many components. So how do we proceed in selecting a suitable mixture model? And selecting a mixture model, you could also think about selecting the cluster kernel you want to use for each of the clusters. How do you want to characterize the clusters? And one decision up front is, can we find sort of a distribution in our mixture model, which we plug in such that each of the components in the mixture model has a one-to-one relationship to clusters. And this would be the easiest, the normal choice, and then people would look at what kind of data do I have? Do I have just continuous data? Do I have categorical data, mixed data? Am I in a regression setting? And then there would be sort of usual choices people would try out in saying, okay, if I have continuous data, what kind of mixture model would I try first to see if I get good solutions, or do I need to select a different clustering kernel? And the alternative is using mixture models for sort of semi-parametric density estimation, and then do an additional step of combining components together to form a cluster. Because this is what people have often observed. You fit a mixture model, you do selecting the number of components with the BIC, and then what you get back, you get this overlap between components, and they don't really reflect the cluster structure. So there have been post-processing steps being proposed, like two-step procedures where you first fit a mixture distribution as a semi-parametric approximation, and in the next step you say which of those components do I put together to form a cluster. Or the alternative would be to already impose constraints on components so they belong together and form a cluster. And we want to look at how would we do these kind of things now with maximum likelihood estimation, and also which kind of packages on CRAN would be available then to fit these models. So if we have multivariate continuous data, the standard model choice would be fitting a mixture of multivariate Gaussians. So that's nice because we know the normal distribution pretty well. This is also sort of comforting if I fit that model and I know how each of these cluster distributions behave. This also gives me confidence in the solution I'm interpreting. And the only problem is if you fit this kind of model and you have sort of high dimensional data, the dimension of your data sort of increases the number of parameters you need to estimate. And what's particularly crucial is the variance-covariance matrix, which has sort of d times d plus 1/2 entries. So this goes d squared, and this is where a lot of parameters go into, whereas in a clustering context, you might even see it as a nuisance parameter. You're not really interested in getting a good approximation of the variance-covariance matrix. You often want to get a good solution for the means, which you might use as prototypes to characterize observations in that group, and you want to partition the data. But getting sort of a really good estimate of the variance-covariance matrix is not at top of your mind, and it uses so many parameters. So what has been proposed is more parsimonious specifications for variance-covariance matrices, and the initial solution was to use the decomposition into volume, shape, and orientation. So you say the whole variance-covariance matrix I can characterize through the volume it has, through the shape, and the orientation. And then we can restrict these. We can have certain shapes and orientations which would induce spherical clusters. And then we can also impose saying, if we have specific orientation, should it be the same overall components, or should it be different between components? So you have equal and unequal or variable over components for each of these three concepts too. And all these different combinations, if you combine this equal, unequal, and spherical, you end up with 14 different models. So you have 14 different models which just differ in how the variance-covariance matrix is specified. And there are 3 packages on CRAN which implement this model class. And mclust would be the one which has been there for the longest time, but it used to include only 12 of the 14, I think. So there was a need to adding all 14, and I think the mixture model, the mixture package was later added, but it included the 14 different models right away. But the mclust people sort of tried to capture up or catch up and have the whole 14 models now covered. And our mixed mode is comes out from the initiative. There's a very active French clustering group, and they developed a standalone program, Mixed Mode. And at some point, they felt it might be good if also our users had access to their tool, and they developed our Mixed Mode package, where they were reusing the methods they have been implementing for a long time in the standalone program. But I think at some point they realized it's easier to be used by others if you're part of the R community than if you have a standalone package somewhere on the internet people can download. And this is what the 14 different models would look like. Normally, you specify them by a 3-letter abbreviation. So you have E or V saying equal or variable, and then you specify volume, orientation, or shape. And you can say you want to have spherical ones, and should they be the same volume, or should they be spherical with different volumes, and so on and so forth. And most of these packages would just try out all different 14 models at the same time, and then just select the one which gives the best fit according to the BSC. And if we use mixtures of multivariate normals to the first 2 examples, we get our solutions back, and we see the one on the left, which would have been easy to solve with k-means 2. This is sort of the EII model. It's spherical and identical volume. But for the one on the right, it's VII. So we still have spherical clusters, but now we have different volumes. So these different compactness levels can be captured in the mixture model through different volumes being specified. This was the first start to how can we get the variance-covariance matrix more parsimonious. And when data became even more high-dimensional, what people started out was looking sort of for low-dimensional approximations of the variance-covariance matrix, and they introduced factor models, or sort of mixtures of factor analyzers. And Paul McNicholas and with colleagues, they sort of tried to take this idea from the decomposition of the variance-covariance matrix, where you can fix certain aspects over components or have them variable, and use the same ideas to come up with a range of different mixtures of factor analyzers models, and that would be implemented in the PGMM package. And what has also been shown is that the normal mixtures sometimes didn't perform well in cases where you had sort of noisy data, because you have these very light tails. Observations which were sort of flying around could deteriorate the cluster solution a lot. So people looked at robustifications, mixtures of T distributions available, for example, in the T-eigen package, but also look at things where the distribution might not be symmetric, and having this skew normal distribution, skew T distribution, having multivariate generalizations of the skew distributions. And this has also emerged from the bioinformatics micro gene expression data analysis, where people observed often, if you look at the data, you have skewness in there, and it's not that clean. And to get the cluster structure you're really interested in, you would come up with a more complex shape of your component distributions, so you get this one-to-one relationship for the latent groups you're interested in. If we have categorical data, this kind of model is also sometimes referred to as latent class analysis. And the idea is it came from latent class analysis was introduced because people looked at categorical data, and it was observed that there is dependence between these variables. And coming up with suitable distributions, multivariate distributions for categorical data which model dependency is not that easy. And the idea is you use this group structure to sort of explain why you have this dependency. So the idea is you have a conditional independence assumption. If the cluster membership would have been observed, within clusters, the variables are independent. So the overall dependency you're observing in your data set is caused by the different groups which are in there. So in some sense, this is a nice model because for each of the dimensions, they are independent, so conditional on class membership, you get the product over your different dimensions. So there is no dependency structure which needs to be modeled. And it's also nice in some sense, if you look at the group-specific success probabilities, this is sort of sufficient information to characterize the group. And there's also different packages in R. So there's one dedicated one for latent class analysis, the Polka package, and the R mixed mode would also cover this case because it was this general purpose mixture modeling tool. And the model I find the most interesting because I always feel it's the one where mixture models really shine and where algorithmic methods sort of fail is if you're in a regression setting. And people tried to come up with algorithmic methods to do sort of cluster-wise regression, but this was sort of always hard to justify and coming up with good solutions where you think the grouping structure comes from observations sharing the functional relationship or having the same regression coefficients. And you can use different kinds of regression models you can put in. You could have GLMs or GLMMs. And this is the package also Andrea was already referring to, which Fritz Leisch originally started writing and which I joined him in working on during my PhD and have been working on since then. But there are also other packages on CRAN which would cover this mixture of regression case, for example, the mixed tools package. And this regression structure that if we use this kind of model, we could extract sort of the grouping structure from the last example we have seen, where we could either say it's connectedness we have seen, or we can also interpret it as sharing functional relationships. If we want to combine components, in some sense, this is something we need to do if we couldn't come up with a cluster distribution for our mixture model. If we fit a mixture of distributions and then the components we found, they don't reflect the cluster structure. We found too many components, the components are too close to each other to really identify groups in our data set. Then the idea is, okay, we're using the mixture model as this semi-parametric tool for density estimation. And then we perform a second step, and this is more like a tree structure, where we combine components we feel are close, and they then together form a cluster. And this has been implemented also in several R packages. The MCLUS package, they even implemented two different methods for merging components. One is entropy-based, and the other looks at the connectedness of components to merge components together and come up with a final cluster structure. And also Christian Henning was working on this merging method, thinking about how could we merge it and when would we want to combine components, when is it still unimodal, if we combine two Gaussian components and things like that. And he has implemented this in his FPC package where he sort of collects things on model-based clustering, which he has developed and worked on. And an alternative I've been also looking at with colleagues in the Bayesian setting is this is something where you can avoid the two-step procedure and where you could use informative priors to some sense already induce information into your estimation which components should be combined together to form a cluster. Because you could also see this as a two-level mixture model, like a mixture of normals. And the problem is to decide on the lower level which components to go together. And the likelihood is sort of unidentifiable with this respect, but you can sort of try to come up with a identified posterior by inducing this information through the prior. And once we have fitted the model, we'll also need some post-processing tools. And the question is, what's also the outcome of the finite mixture model? So people look at the estimated parameters, but in a cluster analysis setting, we might also be interested in the partition we end up with, and we might also want to do inference on the partitions we obtained, how sure are we about the partition, and so on and so forth. And for the cluster-specific parameters, that's where the Bayesians often are struggling, because of the so-called label switching problem. The posterior is multimodal. If the sampling scheme has visited all modes, you would end up with component distributions, so the a posteriori component distributions would all look identical before you resolve the label switching problem. So if you want to do cluster-specific inference, you need to come up with an identified model and try to sort of concentrate around a single mode in your posterior and get rid of the label switching. And you might want to use it to assign observations to new clusters, so you need to have cluster predictions. And if you look at the cluster analysis literature, they have also come up with a lot of quality criteria for how good a cluster solution is. And once you have a partition, you might also use any of these measures to assess the cluster quality. So what do people usually do in cluster quality? One has to admit, if you look at research, a lot of benchmark data sets people are using are normally classification data sets. So there is sort of a known classification, and people then assess how well did they do in finding the same classification using the cluster algorithm. So without knowing the classification, would a model-based approach sort of been able to extract the same group structure, yes or no? And what people then do is they compare the partition obtained with the cluster algorithm with the partition from the known classification. And what's often popular is to use so-called label invariant measures, because if you're in a cluster problem, it's unclear what's cluster 1 and what's cluster 2. This is also referred to as label switching, so you can just reorder all of the components and you end up with the same likelihood. So if you don't want to resolve that problem, it's nice to look at sort of congruence measures between partitions which are label invariant. And there would be the Rand index, Shakar index, or purity as measures you might use to assess the congruence between two partitions. So you could either use this for two different cluster methods and look, if I use different mixture models, do I sort of find a similar partition? Then I can just compare them and sort of get a notion of stability of the induced groupings, or I can use some known classification and try to compare the two. Alternatively, if you resolve sort of labeling issues, you could try to find use a measure which needs that and look at misclassification rates. So more the things you wouldn't usually use to assess the performance of a classifier. And if you look at what kind of tools are available on CRAN, which you can then sort of do after having performed the cluster analysis, may it be using an algorithmic approach or a model-based approach, there's the CLUE package, which try to provide tools for cluster ensembles. which can be used and tries to sort of provide a general infrastructure which can work with different kinds of output models. Because you can imagine whatever package you're using, everyone comes up with their own fitted model object or fitted clustering object, and then using this for predicting new classes, extracting class membership, extracting the partition might be tedious, and you would need to have different methods for all these different classes. And this is a thing that the Clue package tries to resolve, coming up with a layer where you can have the same functions and use them in combination with the different packages. And in some sense, if you have then an ensemble of clustering which you obtained with different algorithms or different mixture models, you can more easily combine, compare them and see, am I able to in a stable way, extract the same groupings regardless of the method am I using, or does, for example, the cluster solution obtained crucially depend on the algorithm I'm using, which often is an indication that there is no real cluster structure in the data, but most methods, if you say, give me 3 groups, they'll just partition the data into 3 groups. And just wanted to also give you some idea of what Fritz and I tried to accomplish with the Flexmix package, and I think of it as a nice implementation in the sense of trying to exploit what the EM algorithm does as a framework. You think of the EM algorithm, the E step being pretty stable once you are able to sort of evaluate the density of the cluster you're in business. Anything else stays the same. And the M step just depending on weighted maximum likelihood estimation, where you can again reuse tools from other implementations. And that was the idea behind the Flexmix package. It implements this general framework for the EM algorithm. And the assumption is we're using it in a model-based clustering context, so we'll have the same component or cluster distribution for each of the clusters or components. So in some sense, you specify the model by what should each of the component distributions look like, and then how many components do I want to fit. And then what the Flexmix package does, it takes care of all the data handling. It sort of provides the E step. And what one needs to do if now I want to fit a new mixture model, I've identified a specific model I want to use for one of the clusters, I need to provide a new M step. So the idea was you can easily extend it, you can try out new types of mixture models, use it sort of for rapid prototyping, have an idea what kind of structure might be in there, what kind of model do I want to use for one of the components, and then you just go ahead and try to only estimate, implement that M step, and then you're able to fit it and reuse a lot of things which are shared, like how do I initialize the EM algorithm? There are different variants of the EM algorithm implemented, and what you get back is sort of this fitted object, which also has certain methods implemented, like print, summary, plot, where the idea is to come up with methods which make sense in a clustering context, regardless of what the specific cluster distribution is you're fitting. And the original motivation was also to provide mixtures of regression models in R, because at that point there was already the M-class package available, so there was no, the idea was not to replace functionality provided by the M-class package, but to have, in addition, mixtures of regression models available. And over time, while I was working on it, also with different colleagues, we tried to extend the package. We added new M steps depending on the different models we wanted to fit. And for example, one setting was we wanted to fit mixtures of linear mixed models with censored data. And that's a data set we use then to illustrate the method. So you have HIV RNA levels of patients, and you treat them. So you start measuring these levels before treatment. So at that point, it's high. Then you start treating these people. And then HIV RNA levels sort of decrease. and at some point you're below measurement accuracy. So you get censoring because you know the true level is lower than the threshold, but you just cannot measure it anymore. And with this data set, it's something which is observed for most of the observations, so it's something you cannot ignore. So you want it to be part of the model because you treat these patients at the beginning sort of all have a decrease in this HIV-VR RNA levels and sort of they hit the threshold. And then if you model this kind of data, the idea would be also at which point do the levels increase again? Because you know there's treatment, people, these levels decrease, but at some point it might increase again. So we tried to come up with a mixture model to identify groups which differ in these development of HIV RNA levels over time. And you see, for example, okay, they all decrease at the beginning, but they have different points in time where increase will start again. And we also tried to match that information with what information is available for a patient before you start treatment, and then the idea would be, could you predict the class membership and see how the different segments differ in how they behave. And this was sort of, we tried to get this into Flexmix, developing the EM algorithm for this kind of model and just adding these steps to estimate. And another idea was we wanted to fit mixtures of linear additive models. Sort of this is time course gene expression data, and you want to sort of find groups of genes which sort of develop similarly over time. So you standardize the expression levels, and then you want to find sort of curves which are shared by groups of genes. And we thought it might be interesting to use an additive modeling approach where the smoothness is penalized in a different way. So you want to have groups where the curve might be smoother than for other groups. And we tried to estimate that, implement that in Flexmix, and then try to come up with a good grouping of the genes where you say, okay, for some, we might even have a solution where you sort of end up with straight lines, so it's completely smoothed out, whereas for other groups, you see it's quite a wiggly behavior. And another work, a colleague of mine, he was working on beta regression models, and then the idea was, couldn't we also combine that with mixtures? So we want to have mixtures of beta regression models, and the idea was, can we not now, there's this beta regression package which fits them, can we not sort of get the M-step working for Flexmix and then get the mixtures of beta regressions doing? And this data set is, you have children and you measure their IQ and how well they do in reading. And you have a categorical variable telling you if they are dyslexic or not. And the idea was, okay, if we would not have observed these categorical variables, in a mixture approach, this would be latent groups. Would we have been able to sort of extract the grouping again? And this has been already tried in the literature before, and we tried to follow their approach. And what's problematic in fitting is you sort of have one group which, regardless of their IQ, is doing pretty well. So they're sort of at the boundary of accuracy. And what we did is we fitted a mixture of beta regressions with an extra component which would capture the observations over there. And then we ended up with a 3-component mixture saying, okay, we have those kids over there, which are sort of perfect regardless of IQ. We have the group where with increasing IQ, they also perform better in their reading accuracy. And then there is this group of the dyslexic children where there's no relationship between IQ and reading accuracy. So to sum up, I just wanted to show you that model-based clustering is a very versatile method. If you are doing cluster analysis and if you have a problem, you're seeing that you might want to also consider using model-based approaches. I hope you have seen there is a range of packages available on CRAN which you could use. And what you might need to decide on if you have a data set at hand is what clustering kernel do you want to use, so which kind of mixture model do you want to decide on, and also what kind of estimation methods you might want to use. Are you more a Bayesian or a frequentist? And then you might want to see what's available for you out of the box to use. But there's a large number of R packages available, and we tried to give an overview. So the Zirand task view on cluster analysis and finite mixture models is done by Fritz and me, and we tried also to sort of arrange things and cover packages. But if we are missing packages, one of yours, or when you're using, we would be grateful if you could drop us an email and tell us about it, and then we'll be happy to add and show to people what's available on CRAN for model-based clustering. And also, this also covers other cluster analysis tools. Thank you very much for your attention.
Just put Slido on.
Great. Thank you, Bettina, for that panorama of everything going on in R for model-based clustering. So I guess we'll start with the top questions. So it looks like the first question here is, how do you deal with the case that you have a more or less nice clustering structure in a subset of the dimensions? So, and I guess that goes for both the low and high dimensional case.
So I think there are two streams in the model-based clustering literature on that. One pursues variable selection. It would say, okay, I have a nice cluster structure in some, then I just pick those and throw the others away. So this would be more of a data-driven approach where I say, okay, people throw data at me, and I hope there's cluster structure at least in some of the variables, and you try a procedure. So there are even dedicated methods which include variable selection as part of the estimation method. And then you would say, okay, I'm just looking, is there a cluster structure at least in a subset of my variables? So that would be one way of dealing with this. And I know that Christian Henning, for example, is against these kind of approaches. He normally would argue that if someone comes with a data to you and he says, or they say, we want to have this data set clustered, the cluster structure should reflect everything that's in the data set. So in some sense, it depends also how well thought out you think the variables which are currently in your data set are, and is it also more an exploratory exercise you're doing with your data set, then you might want to get rid of variables where nothing's going on and at least understand what's going on in the subset? Or do you think there's it's a real application of finding a partition and moving on? The partition should sort of reflect the structure in the whole data set, including all variables which have been sort of carefully selected to be included.
I see. Okay, thank you. So maybe I'll skip down just a similar question just below. So in practice, especially for applications, do you generally try to evaluate whether or not there is even a cluster structure present at all? So whether there might just be a single cluster?
I think that's often the question, do we need more than one group or not? Because then you're in the homogeneous case and you can happily move forward. In other settings, it might be sort of the need to group data. You want to have a partition, and then you wouldn't sort of consider that question. But that depends on the application context. But there are certainly enough applications out where, for example, if you fit a regression model, and you like it a lot and you want to move forward with it, you could also say, okay, I'm also fitting a finite mixture to sort of guard myself against the danger that there might be more than one group. And then you sort of resort back to the simple model and continue with it.
Okay. So sort of bouncing off this idea of high-dimensional data, this is something you touched on a little bit, but generally, what are the performances of these methods when you're working with high-dimensional data?
I think for high-dimensional data, it depends on like if you have continuous data, it would depend on how you specify the variance-covariance matrix. So if you're happy assuming just a diagonal, it wouldn't be that bad. And it also depends on the estimation method you're using. What people have encountered is that the high-dimensional case is sort of tricky in Bayesian estimation. So in the handbook I've already been referring earlier, there's also a chapter on computational methods for Bayesian estimation of the finite mixture model, where they particularly looked at the high-dimensional case and pointed out also more challenges than solutions.
Great. Okay, so we saw that there was the CRAN, or CRAN, depending on how you say it, task view for clustering for all these different packages, but there's this question about the technicality of these methods. So for those that might find this a bit technical, do you have any books with R that might explain some of this in sort of an introductory way?
I think there is a new book coming out written by Charles Beuvron, Adrian Raftery, Brenton Murphy, and yeah, I think so. Yeah. I think it's Wiley. And I think that would be the idea to go there. So it really includes our examples and the whole range of different models which are covered. And I think the idea was to pick up people who might want to have something less technical and also want to get started right away. I personally also like Jeff McLachlan's book a lot, but it introduces you to the theory in a nice way, but then applying things so it doesn't contain any R examples or something like that.
And if I'm not mistaken, I think that first book you mentioned is actually here at the conference. I think we saw it on the table by the Wiley table, so you can check that out.
Oh, cool.
Let's see. Could you say something about your favorite approach to identifying the optimal number of clusters if you're aiming for functional similarity, but you have differing sizes of clusters?
I think the cluster sizes, I wouldn't be worried too much. So the idea would be you don't want to have too many clusters where some are small. This normally also gives estimation problems. So in your estimation, you often also want to get rid of too small clusters, and this is also a strategy which Flexmix pursues by default. In some sense, if you want to fit 10 clusters and some get too small, they are dropped during EM, and you end up with a solution which contains less clusters, in the sense that if I want to use this in an application, no one might be interested in a niche group or cluster containing less than a certain number of observations.
Okay, so we have a next question about the Journal of Statistical Software, so for which you're an editor. Could you give us just a little bit of insight into the submission load, impact, sort of target audience, and so on?
So it's about statistical software, and it should be open source. So the main thing is the software itself, and software manuscript should be reviewed together, and we also have a very strict replication policy. So any results you're presenting in a manuscript also need to come with a replication script. So readers can then have a look at the manuscript, but they can also download the package and the script and try to run through the examples. And the idea is this just helps them getting going. Interesting topics for the journal today. I think any statistical software is of interest. So we focus on statistical software. So sometimes it's borderline. Is it useful for data scientists, or is it really statistical applications or modeling, which is at the core of the implementation, and that would be our general idea is we want a readership which is interested in statistical software. It should be a rather broad readership, so two specialized topics might also find a better audience in dedicated journals than JSS. And, but otherwise, we try to cover a range of statistical aspects, and the idea is also that the manuscripts are written in a way so they're appealing to this general audience. So you pick people up and you tell them about the great method you have, you tell them about their implementation, because some of the readership might also be more interested in the computational details, also in design decisions you have been making on the way, but often we're also interested in saying, just finally also give us an application case, which sort of also in some sense gives readers an idea of how can I use that in the future. Like you read about the model, but the application might give you more of an idea of linking it to something you're using in your own work and saying, oh, yeah, this is a similar structure. I might be able to use that in my own work. Software, anything that's open is welcome, and we also have where the original implementation, like we have MATLAB submissions, so it's only the add-on software which needs to be open source. That's one thing, but otherwise it's also in the review process, it sort of limits the pool of reviewers if commercial software is needed by the reviewer to have a look at it. But everything else is welcome. Certainly, most of our current submissions, I would guess, are in R, but that's not because we're trying to have it that way.
Okay. Well, how about for one final question before the break? Maybe I'll skip down and just ask about some of the applications that you've worked on, and so in particular, some questions that you can answer with clustering. Could you just maybe give us one or two examples of some real-life problems you've addressed using this type of method?
I've been collaborating a lot with a colleague who was in marketing and tourism. We also wrote a book on market segmentation analysis, and there often the idea is in tourism, you have all these tourists, you do survey data, for example, and you try to find groups of tourists. This is interesting for an organization to find out what market segments are out there and how could I best cater to each of them. So this is a collaboration I've been doing a lot together.
Okay, unless there's a word from the local organizers at all, I think it's time for a coffee break. Thank you.